Okay, in this video, this is going to be our video for section 5.3. This will be all of your notes, so update your table of contents, and tomorrow we'll start section 5.4. So 5.3 is about inverse functions. We're going to start by talking about what an inverse is, and we'll do a couple examples, so it's more like a pre-calculus review. And then we'll talk about what happens with, what do we use the derivative of an inverse for, how do we find it, and then finally some AP examples. So the kinds of questions that the AP exam is actually going to ask you. So the first thing is we want to know what an inverse function is. Well, we can define it in a couple different ways. We can define an inverse function graphically through a graph. That's what that means. So graphically, an inverse function, if we have an x and y axis, it's symmetric about the line y equals x. The line y equals x is this diagonal line that I just kind of dotted line. So like, let's take a parabola. That's a graph that we are familiar with. Well, the inverse of this is going to be flipped along that dotted line. And it's going to look like this. So it's going to be a mirror image. Drawing it isn't perfect, but that's what happens. But algebraically, or we can call it analytically, what we actually do when we see an equation, which is more often, we just switch the x's and y's. So everywhere you see an x, you put a y. Everywhere you see a y, you put an x. And then you solve for y, and that's how you get your inverse function. And then we also have notation. Notation for an original function, this is what we usually use. So notation for an original would be like f of x or g of x. So that's just the ones that we normally start with. For an inverse function is noted with kind of, it looks like a little exponent of -1. So that would be the inverse of f. It's not a derivative, it's not just a apostrophe, but it's going to be a -1 kind of exponent on the f or g or whatever function that you have. That's what tells us that it's the inverse function. Now, something to note is that not all functions, their inverse is not necessarily a function. So we figure out if something, so from algebra, we had something called a vertical line test, and they may not pass that. So they may not exist. They might have you dividing by 0 or something like that, or give you too many values for your domain. So that's just kind of like a vocabulary thing. We're going to be talking about a little bit of vocabulary in this section. So just note that, like an inverse would be, so if we had y equals x squared, the inverse or the opposite of that would be y equals the square root of x. We would have a plus and minus in that square root because when we solve, that goes in. But that's what would give us these kind of two graphs that we talked about up here. Okay. So let's talk about finding inverse functions. So to find the inverse of f of x equals 3 minus 4x. Well, our first step is going to be, it's going to be easier to change x's and y's if we change f of x to y. So if we have y equals 3 minus 4x, because our definition is switching x and y, so we want to have a y in there. And then after we switch, after we put that y in, is actually time to start doing our inverse process. So we have a y and an x. So those are going to become the opposite. So we're going to switch our x and y. So this will be x equals 3 minus 4y. So we switched our x and y. So you can make a note of these general steps on your paper if that will be helpful for you. The next step would be to solve for y, because our functions are always y equals. We never have a function that's x equals. So to solve for y, I would move the 3. So we'd have x minus 3 equals -4y. We'd want to divide both sides by -4. When you divide by -4, just keep in mind that you could leave this as y equals x minus 3 to the -4, but most often that negative is either going to come out front or it's going to distribute to both of the terms on the top. So we might have -x plus 3 over a positive 4. That's how you'll most often see. We don't often stop at dividing by a negative. And then our last step, that is our inverse function. Our last step is just to change y to f inverse of x so that we know the difference in notation of f of x and f inverse of x. So our final answer, f inverse of x, is just negative x plus 3 over 4, or either one of those. You could have used either one of those, but I prefer the one without a negative on the bottom. Okay. So that's how we find an inverse function. Switch the x and y, solve for y, basically. And just watch your notation. So the next inverse, let's do this again. So let's follow those same steps that hopefully you made a note of. So the first thing that we're going to do is we're going to put y into this equation so that we can switch x and y. And then we're actually going to switch them. So y becomes x becomes y. We have minus 1. And then we want to solve for y. So I would add the 1. So I'd have x plus 1 equals y cubed. And then to undo a cubed is going to be a cube root. So both of these will be cube root. Only even roots have plus and minus, so those are just going to cancel. So y is just the cube root of x plus 1. And then our final answer, we need to change back our notations. We have f inverse of x is equal to the cube root of x plus 1, and there's really no other way to write that. Let's look at one more instance to find f inverse of x, but this time it's just a table. A lot of times the AP exam is just going to give you a table, and that's what you're going to use. So this first one is x values of -1, 2, 3, and 7, and f of x values of 3, 4, 7, and 5. Well, remember, if f of x is going to be equal to our y values, and to get an inverse, we switch. So that means f inverse of x, you put in the y's, you get out the x's from before. So in order to make the inverse table, it switches. So our y's, this was our y's, will become our x's. So 3, 4, 7, and 5. And our x's will become our y's. So they'll go over where our y's are. So that would be -1, 2, 3, and 7. Because that's what an inverse does. It just switches the x and y values. Okay. So make a note on the side because this is important. We'll be using this notation. If, let's say, like this right here, would be that f of -1 is equal to 3. Well, if we wanted to switch that around, we could also say that that means that f inverse of 3 is -1, which is what we have in this table. If we plug in 3, we get out -1. But this notation specifically is important because we're going to be using it later on when we start doing a derivative of an inverse. Okay. So that's generally everything about an inverse that you should have known coming into this class. There is one other thing that we can talk about. This is mostly vocabulary related that the AP exam will sometimes bring up. So sometimes they will ask you about the existence of an inverse function. So does an inverse function exist? Well, it does if one thing from algebra, so kind of reviewing some more words, if f is 1 to 1, then you have an inverse function. We know something is a function with a vertical line test, but f is 1 to 1 if it passes the horizontal line test. So for example, if we had our favorite parabola, we know what that looks like. And we did a horizontal line test. Well, the parabola itself is a function, but this hits the parabola in 2 different places, so it does not pass the horizontal line test. So the inverse of a parabola is not a function itself. We can undo a squared, but it ends up giving us 2 different functions. functions. The other one that's a more calculus-y word is if f is strictly monotonic. So these are related because like f is 1 to 1, so one x value for every one y value. Well, the second one, talking about monotonic, so mono still means one, but what this word really means is like going one way. So what we mean is either it's going to be all like increasing or flat, it just doesn't have any decreasing parts, or the other way around. So everything is not increasing. I know that's kind of like a weird way to think about it, but we're okay with it being flat. It just can't like switch from increasing to decreasing. We're all not decreasing. And that can be confusing. So we have some pictures here that it would be good to sketch to have an idea of what's going on. So this first one. This first graph is all not decreasing. Do you see how our graph is always going up or flat? We can't say always increasing because sometimes it's flat, like right here it's flat. So technically it's not increasing there, it's just staying constant, but it never decreases. So it never switches to decreasing. So that means it's going one way. So it's monotonic. This is monotonic. This second graph, if we see, then it kind of does the opposite thing. It's always going down or flat or going down. Flat is still okay, but everything here is not increasing. So it's still going one way. You're still on your way to your destination. Now this last one is what most functions that we've dealt with are. They are increasing and decreasing. So this switches from decreasing to increasing to decreasing. So that is an example of something that is not monotonic. Okay, so that's the idea. You really don't have to know so much about this detail, but you just need to know what that word means, because sometimes like when they give us an FRQ and they're telling us all this stuff about a function, they'll be like, and it's monotonic. So we could say, okay, then it has an inverse. Like sometimes they might ask you, does this function have an inverse? They're just checking to know if you know, checking to like see if you know, however that sentence goes, what the word monotonic means. Okay, so now we've gone over it. So kind of look at that, pause the video, ask some questions if you have any, because that can be a little bit of a weird topic. So the reason why we talk about this and the reason why this is about to be connected to derivatives is because if the derivative of this function, if this is always going up, then this means that our derivative is positive because it's always going up. Okay, and in this, if it's always going down, then the derivative is always negative. Because remember, derivative is our slope. And then in this one, our derivative would be both positive and negative. So that doesn't really apply to being strictly monotonic. So either our derivative is all positive or all negative. And we used to talk about this a lot. So this is another review of something that we did in this next example. So an example of a question that they might ask you. Use the derivative to determine if the function is strictly monotonic. So this is a lot of big words, but it's actually going to be really straightforward to solve. On its domain, oh, there's supposed to be an I in there for domain. And therefore has an inverse function. Well, really, they're just asking you to see, is the derivative all positive or all negative, and then write a sentence that says your answer. Okay, so let's see. Well, first, if we have to use the derivative, we have to find the derivative. So f prime of x is 3x squared. Derivative of 1 is 0, so it's just gone. Okay. Now, to figure out if our derivative is all positive or negative, do you remember those sign charts where we'd put a number and we'd see if it's positive or negative or both positive or whatever? That's what we use here. So we're reviewing all of this information that we're going to need for the AP exam within these smaller topics. So if that's our derivative, then what we would do next is take our derivative and set it equal to 0. Because we need to figure out what number is going to go on the number line to check on either side of, and that will tell us what the whole function is doing. So to solve, we need to divide by 3. So we just have x squared equals 0. You can square root both sides. Square root of 0 is just 0. It's not plus or minus because 0 is not negative or positive, so it doesn't matter. So if we're going to make a number line here, we would have a number line with 0 on it, and this is our derivative, remember. So that means when we pick test numbers, so let's pick -1 and 1. When we pick test numbers, they go into the derivative. Well, when we plug in -1, it's going to be squared, so it's positive. We plug in +1, that's already positive, squared positive, times 3 positive, so this is all positive. So our derivative is always positive, except for right here it's negative, or it's 0, not negative, not negative. It's 0, so our function could look something like this. It is always going up, or 0. So what did they want to know? Determine if the function is strictly monotonic. Yes. F of x is strictly monotonic. And we want to say why. Let's try that again. I see something like that. So its inverse, it wants to know if it has an inverse function. Yes. So f inverse of x is a function and the reason for all this is that our derivative, not our derivative, let's say what the derivative is. So f prime is always positive. And that's what we want to answer for that problem. So that's how we can use the derivative to talk about strictly monotonic, which has to do with inverse functions. Now let's actually talk about inverse functions themselves. So one thing is that the definition of an inverse function, if you plug inverses into each other, if we do f of g of x and their inverses, what happens is everything cancels out and you're literally left with x. Like if you put a squared into a square root, they cancel out and you're left with x. So we use that in our derivative of an inverse. When we're taking the derivative of the inverse, well, let's look at this. If this is the definition of our inverse, and we take the derivative of f of g of x, and the other side is x, and we take the derivative of that, just taking the derivative of this equation on both sides. Well, over here we have an inner function, so we have to use chain rule. So we have derivative of the outer, f prime, leave the inside alone. And then we do the derivative of the inner. And the derivative of x is just 1. Well, remember g is our inverse, and we're trying to take the derivative of our inverse, so we can take that, g prime of x. If we want to get it alone, it's multiplied, so we can divide f prime of g of x to the other side. So this means that our inverse derivative of our inverse is 1 over, we use our original derivative and then we use the inverse itself before we take a derivative. So this is a definition that we're going to write down. Anytime you want the derivative of an inverse at a point, this is the most common AP question about inverses. is that if we have g of x, this is what we just talked about, and it's the inverse of f of x. So instead of writing f inverse, we just want to write g because mathematicians are lazy and they want to write as little as possible. So if we don't have to write that little -1, we don't want to. So when we do that, this is what we got. That if it's at a point A, then the inverse, the derivative of the inverse at that point, we do 1 over f prime of g of A. Okay, so this is our definition that we're going to be using for the next couple examples that we do. So we're going to do, looks like 3 examples, one of just straightforward using this, and then we'll do a couple that are more common on the AP exam, and then that'll be the end of this section. So let's look at this. Let's use this to find this. Find g prime of 17. So we need g prime of 17. If g is the inverse of f, so they told us that they're inverses, and we have f of x equals 17x cubed. Well, look at this inverse definition. That is a 17. That looks like it's really 27, doesn't it? We need all of these things. So if we're finding g prime of 17, that means we need 1 over f prime of g of 17. Well, g is the inverse of x. So one thing, if we want to find our inverse, we could switch our x's and y's, but we can also do something else. Do you remember this note that I had you make? They want us to plug in, so they want us to get g of 17. But we don't know what that is because we don't have g. They only give us f. Well, that would be the same thing as what do we plug into f to equal 17? Because remember, these are inverses, so x's and y's are switched. Well, we can easily look here. What number do we plug in for x to get 17? Well, we're already multiplying by 17, so the number that has to be in there for that to stay 17 is 1. So it's f of 1 is 17, which means we can go backwards again and say that g of 17 is 1. So we can use this relationship, and we don't even have to find the inverse. It's a little bit of a shortcut if you know this notation. So, well, we know g of 17. We need g of 17. Well, we can put that in there. So this is 1 over f prime of g of 17. We just figured out was 1. And then we just need f prime of 1. Well, we have f, and we can find the derivative. F prime of 1 means we need to take our derivative, so f prime of x is 17 times 3 is 51. Then we have x, subtract 1 from the exponent, squared. So f of 1 is 51, not 15, times 1 squared, which is just 51. So our answer, without even finding the inverse, is 1 over 51. Okay, so there is our derivative of the inverse without even finding the inverse. So take a second, look over this problem, make sure that you understand it because we're about to use it in a couple different ways. Pause the video, ask questions if you have questions because this is really important. Now the last 2 things that we want to do is we want to look at some AP examples. So what are the kinds of questions that the AP is going to ask? Because they're usually not going to ask for you just to use this formula. What they're going to do is they're not even going to allow you to take the derivative or take the inverse of the function. So let's look at this first one. Let g of x equal f inverse of x. Okay, so these 2 things are inverses. And this is all the information they gave us. If f of 2 is negative 3, and f prime of 2 is 5, find g prime of 3. Well, it's an inverse, so we use our definition from the previous page. G prime of A is going to be 1 over f prime of G of A. So we need, what do we need? We need G of A. So in this case, A, what are they asking us to plug in? They're asking us to plug in negative 3. So G prime of 3 will be 1 over f prime of G of 3. Well, first we need G of 3. So if we can figure that out, so we figure that out the way that we figured it out before. Oh, that's a negative 3. Sorry. Yeah, they're asking us to plug in a negative 3. Let's get that right. Well, if we're plugging in negative 3 to the inverse, look what we have right here. We have the regular function where 3 is equal to, and remember, our x's and y's are switched for inverses. So if we want g of negative 3, then these two are just switched. Well, g of negative 3 is 2. No inverse necessary. So g prime of negative 3, we're one step closer, is 1 over f prime g of negative 3. And then look, they gave us exactly the amount of information we needed to be able to solve this problem. They said f prime of 2 is 5. Okay, well, let's put in f prime of 2. 1 over 5. That's our answer. No taking the inverse, just knowing this definition and this property that we can switch the x's back and forth because that's what an inverse is, and we can find out our answer to this. Okay, so just one step at a time. And there's one more way that the AP can ask us questions. Sometimes they just give us very little information and we have to know this to be able to solve this. Or they give us one of their favorite things to give us, and they give us a table. Where's the table? There it is. Selected values of a strictly monotonic. Okay, this is kind of superfluous information at this point because they're going to ask us to do some things, but all they're saying is that it has an inverse. Remember that word? Function h of x and its derivative h prime of x are shown on the table below. So we have a quick table. X values, negative 1, 0, 2, 4. H of x values, negative 5, negative 1, 4, 7. H prime of x, 3, 1 half, 1 6, and 5. So, two questions. F be a function such that it's the inverse of h. So now f is the one that's being the inverse. So we've kind of switched our letters around. The first thing that they want us to find is f prime of negative 1. Well, f is an inverse. So in order to find f prime of anything, we're going to use 1 over h, because that's the other function this time. Make sure that you use it based on the functions that they give you. And then the inverse h prime, and the inverse goes on the inside, which is not g anymore. Our inverse this time is f of a. So we need 1 over h prime of f of negative 1. Well, how do we find negative 1? If we want f of negative 1 equals what? Well, if h is its inverse, we want to know what do we plug into h to get negative 1. Well, we'll find out what we plug in. The x values are what we plug in. The h values are what we get out. So where do we get out a negative 1? Right here. So what do we put in? We put in a 0. So So h of 0 is -1, which means f of -1 is 0. So this is 1 over h prime of 0. And then we can go to our table to get our last value. H prime of 0, well, here's h prime, here's 0, so we need this one. So we have 1 over 1/2. That's a crazy three-layer fraction, so we need to keep change flip. Keep 1, change to multiplication, flip the 1/2. So that's just 2. So our first answer is just 2. And then we do the exact same thing with the second one. Pause the video and see if you can do it on your own. So to solve this one, if we want f prime of 4 this time, well then that's going to be 1 over h prime of f of 4. Well, we need f of 4 equals what? Well, we need to know what we plug into h to get 4 then, because they're inverses and they swap. Well, if we look at our table, so let's erase what we already have there and see what will be helpful. We need to plug in something to get 4 with h. Well, here's 4, so what we plug in is 2. So we plug in 2, which means f of 4 is 2. So f of 4 is 2, h prime of 2. Well, h prime of 2, we're already on the 2 column, so we go down. H prime is 1/6. So we have 1 over 1/6. Another fraction and a fraction, keep, change, flip. So our answer is 6. These are all of the things that we can do with inverses. You have a quick worksheet. It's just 4 problems to finish. You should be able to either finish this in class or be a very quick homework assignment. So that's all for section 5.3 is over.